should have a little white disc in it. Okay. And that goes in one of the ends. Doesn't matter which end. In fact, it only kind of matters which end. This needs to fit snugly into the tube. If it doesn't, then all the silica gel that you put in here can fall out, and then you gotta start again. So when you go to insert the frit into the column, you want to make sure that it's snug. So if it's loose on one end, flip it over and push it into the other end. Okay? And it's just a press fit, but it should fit really snug in there. If it doesn't fit snug, you can get another one of these frets from your TAs. Okay? So that's what it should look like. Is that easy enough to see or not really? It's like only so-so, right? That a little better? It's as zoomed out as I can get. I don't know if I can do this. That doesn't do it. Yeah, okay. All right, so once you have this, I would say that for the amount of material that we're going to be using, if you use the ruler that you have, you probably want to go somewhere about 10 centimeters up the column. That's 2/3-ish, right? And we're going to use, in these red bottles, there's silica gel. Best place to use this is in the hood. So you can bring your ruler and your column to the hood. I'll turn this around so I can see what I'm doing. And I'm going to fill this up to about 10 centimeters. Give or take. And that one went to 11, not a big deal. Okay. And we're going to use a method called wet packing. It's hard in a lot of columns to get all the silica gel to pack evenly. The tighter that this is packed, the more evenly this is packed, the better the column runs. You can imagine, and you've used TLCs where they're chipped all over the place and the solvent runs up weird or the solvent bubbles up. Same kind of idea in a column, that you want it to be as consistent as possible. Okay? So pour it into the little beaker that you have. And then you can take the 15:1 hexanes ethyl acetate and you probably only need about 5 milliliters. Where you want to swirl it, and you can't see anything there. Good, cool. That swirl just ends up suspending the silica gel in the hexanes ethyl acetate, and you're going to want to swirl it so you can pour it out. If you stop, the hexanes, you'll see the silica gel settle to the bottom, and then you'll just get a kind of a thick pad on the bottom of that silica gel. So if you swirl, okay, and then carefully pour, you want to get as much of that silica gel as you can in there. Okay. You don't have any compound on the column yet, so having it drip on the table is not a big deal. And then you can either try to pour that again in the top here, or you can swirl. You're going to end up not being able to transfer all the silica gel. It's next to impossible, right? So that's why 10 centimeters, give or take, gives us the buffer room to be able to not have all the silica gel end up in the column. So you can use a pipette. I'm kind of swirling and hosing the solvent back into the beaker. Just to try to get as much of that silica gel as I can. And you can see the silica gel ends up settling to the bottom. And that's enough to give you pretty good packing of silica gel in the column. Now this drip rate, this would drive me bonkers if I'm trying to wait, if I'm trying to get something to happen in an hour, it would drive me nuts. Okay? So that's where this comes into play. Now, this is easy to use, but also kind of easy to screw up when you're using it on top of the column. You only ever want to squeeze this when it's on the column. You never want to let go of your fingers. Because if you let go of your fingers, like a pipette, you're going to try to suck air up in the bottom, and it's going to disturb the silica gel. It's not the end of the world. Plenty of people are going to do it. Just try to avoid it. And so in order to make that happen, okay, just hold the pipette bulb on top of the column and squeeze. And squeeze until there's just a little bit of solvent above the top of the silica gel, and let it settle to the bottom. Next step, the mixture material is already calibrated in here. So all you got to do is take a single pump of this stuff, and that pump into a disposable pipette tube, disposable culture tube. That's all you need. And this is the material that we're isolating, already dissolved in the same solvent that we're going to use to run the column. If you were to dissolve this material and say, we're using 15:1 hexanes ethyl acetate, if instead you were to dissolve that material in pure ethyl acetate and put it on the column, it would just run, all the material that you put on the column would just run with that 100% ethyl acetate right to the end. So what we're dissolving it in is actually important. And we've taken that guesswork out of this part of the experiment for you. Okay. And you want to carefully add the material to your column, trying not to fluff up the silica gel that's at the top. You want that to be a nice firm line, in the same way that you wouldn't put, by TLC, you wouldn't spot your material here and then kind of smear it all over the place, right, which is what you would do if this silica gel turns over. If it turns over a little bit, also not a problem. Right? This is the first time you guys have done this kind of thing, so it's practice. Right? Then to keep the silica gel from turning over, I'm going to use just a little bit of sand, probably a couple millimeters worth of sand. But sand's heavy enough that when you add solvent, it doesn't churn, and it keeps the material that you just put on the column pretty much right where you want it. So a couple of squeezes of that. It looks like that. Okay. So there's some space above. We got our compound that's on there. We're ready to go. Now, as far as collecting samples, I was not quite done with getting all the material off, and I didn't fill 12 of these. I essentially filled 12 of these to about here. Essentially all the solvent that I could fit on the top, I collected as one fraction. The order that you collect stuff in doesn't matter. I'm a zigzag person, other people are typewriter people. However you want to collect so you can follow, I started here, I ended here, kind of deal. That's all that matters. And you can set your column so that your test tube rests underneath with enough space to swap. If you lose a drop, that's fine. It's not a big deal. You're not going to lose all the material that you have on there by just losing a single drop. Okay? And then you're going to use the 15:1 hexanes ethyl acetate to elute everything from the column. Questions so far? You can pour it from your grad cylinder if you want. For me, I feel like it's easier to do with the pipette. I stole an extra pipette bulb. So my first fraction, I'm going to squeeze until the solvent is about at the level of the sand. You can squeeze till it's just above or till it just stops. And then take another test tube and just swap it out. If you wait all the way until the solvent is at the sand, the level of the sand, then you'll see that the dripping stops. So if you're worried about losing material, which on this scale and for this experiment is not really important, but if you had spent 6 months making something, and this is the column that you were running to purify that something, you would probably be a little bit more careful. Notice hand still pinching on this thing. So take it off on purpose, move it away before I swap. That way I don't suck air back up and into the column. And I'm just going to keep doing exactly this. Maybe 10, 12 fractions. Like I said, the column that I ran a little earlier was 12 of these fractions. I think I put in, I don't know, either 20 or 30 milliliters of solvent. And then TLC. So I'll just do one more and then I'll take a TLC just to show you where we're at. Now you can, when you're doing TLCs of these columns, you can start from the beginning and you can TLC every single fraction if you want to. I think with the length of time that a TLC takes and the information that you're going to get out of it, it's not really worth TLCing every single fraction. So you can TLC every other one. You can TLC every third. I'm only saying thirds because this is 3 rows, so it's easy for me to keep track of what's fraction 3, 6, 9, 12, you know. With the other test tube racks, maybe it's easier to do 5s, 6s, whatever the test tube rack is set up for. Whatever keeps things straight for you is, I think, the best thing to do. If we had compressed air on the bench top, you could be using that instead of essentially the compressed air that you're getting out of pipette bulb. You could take full fractions instead. So I'm taking these little, you can call them, I guess, half fractions. I don't know, it's not even a third of the way full. But and depending on the separation of the material that you're chromatographing, the material that you're trying to isolate, it may be totally fine to separate or to take full fractions. And if you have one compound that when you run the TLC, it stays here, and the other compound is way up there on the TLC plate, probably going to be very easy to separate those materials. But these right next to each other are going to be a little bit harder to separate. If they're any closer than that, it's going to be even harder. All right, so I've got 7 fractions. I'm going to leave that one under there. There may be a couple of drips that come out of there. And for TLC, I'm not concerned with calculating RFs. I already know what the RFs are because I ran the reaction. In this case, we didn't, but if you were running this column after running a reaction, you would know exactly what you would expect for RFs, and they're going to show up in the same way on the TLC plate. So what I do on the TLC plates, I tend to not even draw this line. Maybe it's bad form, but I tend not to draw the line on the bottom. And I just put as many hash marks as I can possibly fit on the bottom of the TLC plate. So this one, I can probably get 4 spots. You only need, one TLC spotter to spot all these fractions. Okay? You could actually probably survive with 1 TLC spotter for the entirety of the semester if you didn't break it or lose it, because you can wash these things out. The TLC spotter, I'll spot first one. My MO is to just dab this on my wrist. I just dab it on my sleeve. That's probably bad enough not to show you, so I won't do that. Even though I kind of just did that. So just grab a paper towel There's 3. There's 6. And I'll just do 7 so I know. And then you can write the numbers either before or after on the bottom of the TLC plate so you know what fractions are what. Probably not a big difference between 3 and 7. When I ran this TLC a little earlier, that TLC showed me that 15 to 1 is actually a pretty slow solvent system for these two compounds, meaning that they have a pretty small, pretty low RF. In fact, the compound that has the smaller RF doesn't even come off the baseline really in this 15 to 1 ethyl acetate mixture, or 15 to 1 hexane ethyl acetate mixture. When you're waiting for this TLC to see if you're done, if you want, because it's not that hard to do, you can be running a TLC and you can be getting some more fractions, because you got to wait for the TLC anyway, right? And maybe you're not done. The amount of solvent, the extra solvent you're going to use is not that critical. You'll find in putting the TLC or the pipette bulb on top of the column, you have to find the right angle so that it actually seals on the top. Otherwise, you'll just be squeezing it and not getting anywhere. If you knock a fraction over and it ends up on the bench top, welcome to the club. You can be more careful. You could clamp and unclamp every single fraction with another clamp. And if that material was important, really important, you might want to do that. I don't like using the test tube block, because the test tube block, they're not fixed in there. They kind of all move around. So if I bump the test tube block and now the thing tilts over, now I'm not catching any solvent. So I find I have less disasters when I do it this way. And as long as I have the column down far enough that if I hit the top of this, I'm not going to knock it over, then it's usually pretty good. So there's a TLC plate. What you can see is that in fraction 1 and in fraction 3, you don't see anything because nothing came out of the column yet. In fraction 6, I would say there's actually probably a little bit of both compounds. At least from down here, it's a little bit easier to see than from up there. But for our fraction 7, you can already see that there's another compound below the big spot. So the big spot is whatever is higher RF, and then there's another spot right below it. They're distinguishable, but those are mixed already. So that means that I'm probably going to need another, I don't know, 5 or 10 or maybe even more fractions to get everything off. I'm just going to do exactly the same thing that I've done so far until I get everything clean. I would go back, because I don't know what's going on between fraction 3 and fraction 6, and I'd probably re-spot fraction 3, 4, and 5 to see when is that material coming off and do I have a clean fraction that I can use for NMR. If I don't, that's okay. That's why we're running this experiment, for you guys to get your hands wet in actually running a column in the first place. So I'm not so concerned with exactly how many fractions do you get clean. In fact, I expect you not to get clean fractions. That's not uncommon for running columns. You can change plenty of parameters in running columns. You can change the amount of silica, you can change the solvents that you're using, you can change the ratio of solvents that you're using to get a better separation. But for us, this is a good start. It shows what we normally get when we run columns, or what we can classically get when we run columns, with really all of the mechanics of what it takes to run a column. questions to hear? All right, so let's assume I've gotten everything off the column, I'm done. The next thing to do is to take care of getting rid of the silica gel. So to do that, push the rest of the solvent out of the column. A couple of squeezes of the pipette bulb will do the best it can to get that stuff out. And then you're going to have to carefully take the bottom piece stopcock out. There's some silica gel in there. You're going to knock that into a waste container that's labeled silica gel. And same thing with the silica gel that's in here. The drier this is, the easier it is to get out. But otherwise, you can just use a wooden applicator and kind of start digging it out and knocking it into the silica gel waste. Dig some more out, knock it in until it's all out. It won't take you more than a couple of minutes to do. Then you can rinse it out with acetone and put it back in your drawer and you're good to go. And that's cleaning this out. The silica gel doesn't go in the trash. Okay? Silica gel, the reason that we're using this in the hood is that if you spend a lifetime of inhaling this dust, you would not be a happy camper. And if this ends up in the trash can, the people that come and take care of the trash, they're subjected to the dust that's in here. We want to keep it in the solid chemical waste. The mixed fractions, if you want to hang on to them, you can. Okay? I think the other thing that we're trying to do is find out how much material did we put on. And so there's 200 milligrams total that we're putting on this column. How much did you get back off? And so that total would be whatever your purified compound A and purified compound B is. You get a mass of those, plus the unpurified mixed fractions. Once you have all that material, it tells you how much you recover. That can be really useful for some columns because not all compounds are stable to silica gel. Silica gel is a little bit acidic. And so you might be running a column trying to isolate this material that's important to you, but it's undergoing some sort of a reaction on the silica gel itself. Plenty of reactions we know are acid catalyzed reactions. So you've got a reagent, it's not even a reagent, just the silica gel that's a little bit acidic. It could be chewing into the compound that you have. You may want to worry about that and actually try to figure out, okay, how do I purify it in some other way? So for us, we're just wanting to look and see how much did we put on and how much did we get back off. Other questions about this? Yes, so the other thing that we're going to do with the clean fractions, or whatever clean, maybe you get one, maybe you get a clean fraction of one compound, maybe you get clean fractions of both compounds, doesn't matter which one, or if you get one or both. Whatever you have that's clean, I want you to get an NMR of it. So you're going to rotobat that down, you'll get a mass, and then you'll submit an NMR. Because we're going to use NMR to decide, is this the top compound or is this the bottom compound in RF from what we see on the TLC plate. So we can assign that from knowing which spot is which on TLC, and then taking that spot, rotobapping it down, and getting an NMR. And we can tell these two compounds apart by their NMR. So we're going to talk about how we do that next week in lab lecture.
So if we get no clean fractions, should we just start over?
Nope. No, if you get no clean fractions, that's what happened. Right? That's the thing that you're going to record. And then we'll see, depending on how many people end up in that boat, typically the second compound comes out a little bit more cleanly than the first compound. So depending on how many people end up in the boat where everything is mixed, we will figure out how to address that next week. But we won't know until this week is done.
How many fractions should you do until you get clean?
So you're only going to be able to take so many fractions until all the compounds off. So you'll see that you're taking fractions, and when you TLC them, there's nothing there. The easiest way to do that is actually just to have a piece of, or a scrap piece of TLC plate, and you can just make a whole bunch of spots with numbers on them. And if you see UV activity, you know that there's something there. If you don't see any UV activity, right, towards the end of taking fractions, you know that there's nothing left on the column. So you're done. My guess, probably within 15 to 20 fractions, you'll get everything off the column. Of these